In this video, I will discuss the JEE Advanced PYQ from the topic thermal physics. This question is based on work done by a gas when it expands or contracts. Let me consider a simple system, a cylinder with a piston So the gas is here in this enclosed volume. The walls of the cylinder are rigid, but the piston is free to move. So the volume of this gas can change. Let the pressure of the gas be P and let the volume be V, this part of the cylinder. So the piston moves towards the right, the volume will increase, and when it moves towards the left, the volume will decrease. So it's expanding, the piston is moving towards the right. So work done, so when it's expanding, work is done by the gas. And this work is done on the piston, and work done is F dot ds for a small displacement ds. So the force acting on the piston is due to the pressure So that force will be the pressure into area of the piston. Piston have an area, let it be a circular piston, and it's towards right, and the displacement is towards right. And let my x-axis be towards right. So when this thing displaced by an amount, say dx, the piston is moved by amount dx. So the increase in volume is this much, that is A into dx. So this is the increase in volume. So this will become P dV. So the work done by the gas when it's expanding is P into dV. This for a small displacement dx. Similarly, when the gas is contracting, that is when it's getting compressed, the piston will move towards the left. So in this case, the work will be done on the gas. Obviously, when it's expanding, the gas is pushing this piston, so gas is doing the work. When it's getting compressed, the external thing is doing work on this gas. So work is done on the gas by the piston. So the piston will exert a force on this gas in this direction. So we'll hold this. So the force exerted by the piston on the gas will move in this direction, and the piston will move towards left, opposite to what when it happened when it was expanding. So the new position of the piston will be here, somewhere here, and this is the displacement dx. So again, the work done on the gas is F dot ds. So the force acting on the gas is pressure into area, that's towards left, and the displacement is also towards left. To do it more rigorously, x-axis towards right. So I'll choose one more axis which is towards left. Let me call it x1 axis. So there is a displacement is dx1. Okay, and dx1 and dx are opposite, so dx1 is minus dx. And the change in volume dV is always A into dx. So this will become minus P dV. dV is A into dx. So work done on the gas is minus P dV. So it's contracting, dV is negative. So work done on the gas is positive, which makes sense because when it's contracting, work is done on the gas. So work done by gas when it's contracting is negative of this one, which is P dV. So work done by the gas is always P dV, whether it's expanding or contracting. So the formula is same. Work done by the gas when the volume changes by amount dV is P dV. But it's expanding, dV is positive because dV is final volume minus initial volume. When it's expanding, final volume is more, so dV is positive. When it's contracting, it's getting compressed, so dV is final volume minus initial volume, which is negative. So this is a negative quantity. Pressure is always positive. So work done by the gas when it's contracting is negative because work is done on the gas. And when it's moving from initial to the final state, so this is the initial state, and finally the piston has come here when it's contracting. Okay, so in between the pressure and volume of the gas will keep changing continuously. So if we plot this state of this gas in PV diagram, for example, when it's contracting, the volume will decrease. So initial volume will be somewhere here. And when volume is, say, the pressure is increasing, so it will go like this. So this is the final volume, and this is the initial pressure, and this is the final pressure. This is the final point, this is the initial point. So the in-between states will be somewhere here on this curve. So this path on this PV diagram, when it goes to the initial point to the final state, is called process, thermodynamic process. So from this final state can go still further. If we consider, for example, it goes like this, say final 2, and it's coming like this, say to this point, let me call it the third state, final 3, and finally the final 4 is same as the initial state. So the process is like this. This is the first process, second process, third process. So this set of 3 processes, the final state is same as the initial state. So this entire thing is called cycle. So cycle is a collection of process where is the initial state and the final state are same. So it's a closed path. Process is a path in the PV diagram, and cycle is set of process where the initial state and the final state are same. So it's a closed path on this PV diagram. So the work done for a small displacement is PdV. So the work done to go from initial state to final state, go from initial to the final state, will be integral PdV from the initial state to the final state, because the work done dW for a small change in volume is PdV. To go from here to here, we have to find the work done for small displacements, small change in the volume, and add them. That's basically integration. So the work done to move from initial state to final state is integral PdV from initial state to the final state. Let me consider one particular special process where the temperature is same when the gas moves from the initial state to the final state. That's an isothermal process. Iso means same, thermal means temperature is same. For isothermal process, the work done to move from initial state to final state is integral to final state of P dV. And let me consider this gas to be an ideal gas. So since it is ideal gas, this gas equation for an ideal gas, which is PV equal to nRT, P is pressure, V is volume of the gas, N is number of moles of the gas, how much gas is there inside, R is the universal gas constant, T is the temperature of the gas here. In this isothermal process, temperature is constant throughout. So this I can write as P can be written as nRT by V dV integral. So since the isothermal process from initial to final state, the temperature is constant throughout, so T can come out of the integral sign. So this will become nRT. N is number of moles is constant. R is universal gas constant, that's also a number. So it's integral dV by V, which is ln natural logarithm V between the limits initial and the final state. So it will become V final by V initial. So this is the work done for an isothermal process. So with this understanding, you can solve this JEE advanced question. 1 mole of an ideal gas undergoes two different cyclic processes, 1 and 2, as shown in the PV diagrams below. In cycle 1, process A, B, C and D are isobaric, isothermal, isobaric and isochoric respectively. In cycle 2, process A prime, B prime, C prime and D prime are isothermal, isochoric, isobaric and isochoric respectively. The total work done during cycle 1 is W1 and then during cycle 2 is W2. The ratio W1 by W2 is this cycle 1 in PV diagram A, B, C, D, and here cycle 2 A prime, B prime, C prime, D prime. This is a simple question. You can pause and run this question. Here's the solution. Work done in cycle 1, that's the work done to go from here to here and then here and then here and then come back. This is the work done to go along the process A, that's work done to go from here to here, plus the work done in process B, that's the work done to go from here to here, plus work done in process C, plus work done in process D. And work done is nothing but area under the curve, because it's integral PdV. Integral PdV is nothing but area under the curve. So process A, the area under the curve is this much area, this rectangle. So this length of the rectangle is 4p naught into the width of this rectangle is v naught, because it's 2v naught and then v naught. So this one is v naught. B is an isothermal process. Process B is isothermal. For isothermal process, it's not easy to find the area under the curve because this is an arbitrary shape. So instead of that, we can use the formula of the work done in isothermal process, which is pressure into volume product. So it's pressure P1 V1 of this point, initial point. So 4p naught into 2v naught. So 4p naught into 2v naught into logarithm of the volume ratio. Final volume is initial volume. Final volume is 4v naught, initial volume is 2v naught. So it's ln 2. And work done in the process C. Its area under this curve, this area, this rectangle. And it's negative area because dV is negative. Area under the curve, it's positive when going from left to right. Pressure is positive, so dV is positive going from left to right. But PdV area, it's negative when it's going from right to left. Volume is decreasing. So this area is the direction is this way. So it's a negative area. So you have to put a negative sign here. This area is negative. This much is 3v naught. And this thing is 2p naught. So this area is 3v naught into 2p naught, negative sign because the area is going from right to left. And area under the curve, d is 0 because dv is 0. So this area is 0. So the fourth for work done for process D is 0. Volume change is 0. Work done is PdV. When dV is 0, work done is 0. So in this process, the volume is constant. So there is no work done. So this is equal to 4 minus 6 or minus 2. I'm combining these two. P naught V naught, and then 8 ln 2. P naught V I can put commonly outside. So similarly to the cycle 2, the work done in cycle 2 is work done in the process A prime plus work done in process B prime plus work done in process C prime plus D prime. So the work done to go from here along this path is the work done to go from here to here, and the work done to go from here to here, work done to go from here to here, and the work done to go from here to here. So WA prime is an isothermal process. A prime is isothermal. So we'll use the formula for the work done, which is P1 V1, the initial volume into the initial pressure, or 4 P naught into V naught. So 4 P naught V naught into logarithm of the volume ratio, final volume by initial volume. So it's 2 V naught by V naught. That's 2. On the process B prime, the work done is 0 because the change in volume is 0. It's a constant volume process. The area under this curve is 0 width. So work done is 0. Process C prime, the work done is the area under the curve, this much area. So height is P naught and the width is also V naught. So P naught V naught, but with a negative sign because volume is decreasing. Area under the curve is negative while going from right to left. Because area under the curve is PdV. When going from here to here, dV is at any step it is negative. So add all the negatives, the total sum is negative. And then the fourth work done, D prime is again 0 because the change in volume is 0. So this fourth term is also 0. So it's minus P naught V naught. So minus 1. And then this is 4 times ln 2. P naught V naught is common outside. So comparing this thing, so this is work done in the first cycle by 2. So from this I'll get the ratio of the work done in the 2 cycles, W1 by W2 equal to 2. So the answer to this question is the ratio of this work done in the 2 cycles, which is 2. Two is the correct answer. So this is what I explained here. Work done in cycle 1 is work done in the processes A plus work done in process B plus C plus D. Because work done in cycle is sum of work done in all the paths that form the cycle. So work done in process area under the curve is a rectangle, and work done in process B is also a rectangle. Sorry, B is isothermal process. Area under the rectangle. B is isothermal process. So, this is the formula. Work done in isothermal process is the P1 V1 product of pressure and volume, and then logarithm of the volume ratio. That's ln 2. And then work done in process C is area under the rectangle, but it's a negative area because going from right to left, dV is negative. And process D, area under the curve is 0 because dV is 0. It's a thin rectangle where one side of the rectangle is 0 size. So in cycle 2, the process A prime is isothermal process. So we use the formula for isothermal process, which is P1 V1 and then logarithm of the volume ratio, which is 2. And process B prime, area under the curve is 0, and also D prime is 0 because change in volume is 0. And for C prime, it's area under this curve, which is the area of this rectangle, which is P naught into V naught, but negative area because dV is negative. So comparing this with the first one, we get W2 as W1 by 2. So that means the ratio W1 to W is 2.